Welcome back, everybody. We are now on activity 7 for today. I hope this thioacetal looks familiar because we just made it. And in an earlier video from today, I said there's something aldehydes can do that ketones can't. I want to remind you, this came from an aldehyde. Previous video, this was an aldehyde. Previous video. Somebody needs to mute. Previous video. We did this to this. This is an aldehyde. You don't have to show that on this video. Okay. Now, if this was a ketone, there would not be an H up here. Okay, if there'd be a ketone, that'd be another carbon group. So this H is not accessible if we started with a ketone here. We did not start with a ketone. We started with an aldehyde, and we have a new pKa. New pKa. Right there. 30. It has to be from a thioacetal that has an H on the carbon that is the thioacetal carbon. Otherwise, there's no pKa if there's not an H here. Learn it. Put it on your pKa table. All right. What are we going to do with it? Apparently, we're going to do acid-base with it. That's why we talk about pKa's. All right. Get rid of your spectator. Put your lone pair. Hey, this is the hydride that we've been using before we learned about sodium borohydride this morning. This is the strong base hydride. And whenever you see KH, you should be thinking this is a base. Okay? So acid base is it. You can't combine this step with anything else. It's pink because I already had red on the screen. And that's going to give us some exciting prospects here. Lone pair minus, if you're a synthetic organic chemist like me, and you can generate a carbon that has an anion, you're very excited. Because you know you can do some synthesis now. I just need a carbon that's got some positive character to it. And this thing's going to say, yes, we can hook up. Here we are. And you are done with this first part of this mechanism. Nice. Yeah. And you made that's a red bond between two carbons, synthesis. Yeah. Yep. So next one is not so simple. There's a lot going on. Not only is it hydrolysis, it's there's an acid base step. As well. And the acid base step puts this H here. I'll do that first. Lone pair. Please don't attack water. Please. That'd be a grave error. pKa 5 reacts 10 to the power of 5 minus 10 to the 21 times faster than this H. So please don't react the wrong H. All right. So after you've protonated it, we can worry. That'll put the green H on there. That part's done. Now we got to worry about getting rid of our acetal. That's called hydrolysis of acetals. We're going to use water. And what's water going to do? Well, water provides this oxygen here. That oxygen is not going to attack this carbon unless this carbon has some a better positive nature. If you're bonded to sulfur in your carbon, do you have a positive nature? Talk to me. No, you do not. The electronegativities are the same. Even if these were oxygens, that really doesn't change this story. The truth is you've got to get rid of the sulfurs. Got to get rid of the sulfurs. Here's your side product. I want to refresh your memory about your previous video where you used that molecule to create the thioacetal, and now we are uncreating it. We're breaking it down to the original carbonyl. Except the original carbonyl's got this exciting new bond right there. So you need to get an activated thiocarbonyl. Here's what you do. You got to activate the leaving group first. How are you going to do that? I'm going to use sulfuric acid. That's what I'm going to do. No. H is bonded to O, is bonded to S, is bonded to 3 O's. One of them has an H. So we're going to have 3 colors going. Oh, you can't use red. No. Red first. How about that one? We just do this from now on. Wow. And third is whatever after blue. So we're on blue now. And now you can move to a new color and kick off your leaving group. What was my third color before? I can't remember. Dark blue? Why not? Kick off your leaving group. I know there's a lot going on there. Activate the leaving group. Make the leaving group leave. Get some R groups going here, or just at least this R group. That part's done. You've got R attached to this that has 2 bonds to sulfur. Oh yeah. Nope, don't forget your propyl. There you go. 1, 2, 3, 1, 2, 3. Hey, it's an activated carbonyl. It can be attacked by a poor new. Time's ticking, I know. Can we get it done? That's the question. A little ambitious with 8 activities in my mind. It's okay. We're only going to get 7 done today. Ties our record, doesn't it? There's your water. Haven't used it yet. Gonna use it now. Oh, don't draw it like that. Here, redo it. Sorry. I see a way to shorten up things. Can I get to the end? That's the question. No, I can't. End. I have to get to the hemiacetal first. Hemiacetal. I want to remind you, you made this in your previous step. Poor nucleophile can attack an activated carbonyl. Yeah. And you get a hemiacetal if you deprotonate the result. Deprotonate the resulting oxonium. Okay. Then we gotta blast off to finish. Oh, we're gonna be fine. Propyl. No, what am I doing? Propyl. Oh, right. We got the green. Still got sulfur hanging on. We got an O. It's an H. I think I can get to the end. Remember, water has to, no, we're using water. We're going to make a carbonyl. I got to make that sulfur leave. What did I do to make the sulfur leave last time? I had a strong acid. I need to get this somewhere else. Then I protonated it. That's not going to get rid of it. Lone pair in the O makes carbonyl, new color. You're going to be left with the product, but it's protonated still. So you're going to need sulfate ion. This is going to lead to sulfate ion. Big finish. Third color. Third color, not blue, not purple. Grab that H. And this is called deprotection of the carbonyl. You need to read about why we had to make this thioacetal so that we could do the synthesis and then get rid of the thioacetal, because you can't do this synthesis straight from the aldehyde, which makes this thioacetal very useful. And please do not misread this statement, new pKa 30, and think that if these are oxygens, based on what I said earlier, and sulfur doing whatever oxygen does, if these are oxygens, this pKa is not 30. It's not. You can't take that H off. The only way you can take an aldehyde H off, which is this H right here. I know you want to see the whole screen because he's talking and you're finishing. All right, the only way you can take this H off is to first do what we did. Make the thioacetal. Then take the H off. Then attack whatever electrophile you want. Could even be a carbon with a leaving group. SN2. Very good carbon nucleophile. And then protonate to make the alcohol right here. And then deprotect. Get rid of the thioacetal. Get your carbonyl back using this mechanism here. Then I got stuff covered up. I think everything's showing there. Look at that, a whole minute to spare, not really. 10 seconds, and then I'm gonna ship out. I'm gonna come back at 10:10. 10:10 to start the last two questions of Fall 21, Test 1. So the very last two questions. So you might want to get a copy of that going. These will not be assignments at all. This will be straight up tutorial, helping you solve those problems. Okay, so I'm gone, and I will see some of you. It's an optional segment coming up at 10:10. Same Zoom, okay? So yeah, nothing's changing.